Representing patterns in nonlinear functions. Alright, the table shows the total number of blocks in each figure as a function of the number of blocks on one edge. Okay? This is the corner of a block, this is an edge. So as you can see, this block has 1 as an edge, 2 as an edge, 3 as an edge. Really should use green there, please. Alright, so 3 on an edge, right? So again, the table shows the total number of blocks in each figure as a function of the number of blocks on one edge. So the first one, the number of blocks on one edge, 1. The total number of blocks was 1. We have the ordered pair of 1, 1. In the second figure, right, we said 2 blocks on one edge. Okay, total number of blocks is 8 total. This one, this one, this one, this one. We can see the top 2 here, and then there's 2 back here. All right, so there's 8 total blocks there. Okay. Here, for the third one, we have 3 blocks, right? So 1, 2, 3, and then it goes down 3. So 1, 2, 3, 4, 5, 6, 7, 8, 9. And those 9 blocks happen 2 more times, right? That is 27 total, because 9 times 3 is 27. So with 3 on an edge, there's 27 total blocks. So we want to figure out how many total blocks there would be with an edge of 4 blocks, and how many total blocks there would be with an edge of 5 blocks. Okay, it says, what is a pattern you can use to complete the table? Represent the relationship using words, an equation, and a graph. All right, so we know it's going to be 4 comma something. We know this is going to be 5 comma something. All right. If we look at this, we're trying to figure out the relationship of how 1 can get to 1. Well, we can't. We would have to add 0, right? That's the only way we can do that. Or we'd have to multiply by 1. But we have to use the same rule for 2, right, to get to 8. All right, so that kind of changes things. We can't add 0, that's out. We can't multiply by 1, that's out. All right, well, let's maybe look at the rest of the table. We see that 3 is getting to 27. Well, I can kind of think that, well, hey, I know that 3 cubed, that 2 cubed is 8. And I know that 3 cubed is 27. And 1 cubed will be 1. That can kind of help me to lead to my formula of being y equals x cubed. And later on in this chapter, we'll really break down how we can figure that out from the table. Right? But if you think about it, right, it's a cube. Right? We're almost finding the volume of this. Remember, volume is like the length times the width times the height. Right? This is a 1 by 1 by 1 cube. This is a 2 by 2 by 2 cube. This is a 3 by 3 by 3 cube. So it's 3 to the 3rd power. It's 2 to the 3rd power. It's 1 to the 3rd power. 4 to the 3rd power would be 64. So there would be 64 blocks with an edge length of 4. 5 cubed is 125. So it would be 125 total blocks. Okay, with an edge length of 5. The total number of blocks is the cube of the number of blocks on one edge, x. Your equation is y equals x to the 3rd power. We start to plot our points, okay, and see what this graph would look like. On the x-axis, okay, you're talking about the number of blocks on edge. On the y-axis, you're talking about total blocks. And we can start to plot these points. We had 1, 1, 2, 8, 3, 27, 4, 64, 5, 125, 6, 216, which would be like way up higher here. Okay, and we can start to see our graph looks something like this. Now, the interesting thing is to think about this graph. Where would it be if we had 0 blocks? What would the total amount of blocks be? Well, that would be 0, right? There's no blocks. There's no blocks on one edge. There's no blocks, period. It's even more interesting to see what would happen. So we know it goes through 0, 0. It would be even more interesting to see what happens if we had negative numbers. Now, it's not possible in the real life situation to have negative numbers with this real life situation that we have. But in a function rule of y equals x to the third power, and there we have it. It's actually a mirror image going into the third quadrant. Right, this is called an asymptote. We have the point at 0, 0. We have 1, 1, which is, so here's 1, 1, sorry. We have the 2, 8, which would be right here. Okay, and you would actually be able to follow all those points. This is what the graph would look like. Now, we don't need this portion of the graph because, again, we're dealing with a real-life situation. We're talking about the number blocks on an edge. But it's interesting that when you have a graph, x is the base, like the variable is the base, and you have a number, like 3, as your exponent, it's going to be an asymptote. Depending on what the exponent is, it will change the shape of the graph. For example, if the exponent was 2, and now it's like a U. Okay, that's called a parabola. All right. If it's 4, it changes again even differently. It's just going to. We're zoomed out a little too far. We can't really see the shape of it. Okay.